All right. We are going to play a game. You're going to need a partner. We have 19 people in the room, so somebody gets to be my partner. We want groups of 2. Once you have your group of 2, I want you guys to come up, or one person from your group to come up and grab a paper bag, and then I will explain the rules of the game. So find a partner, come get a paper bag. If you do not have a partner, can you raise your hand for me? Okay. You guys want to partner together? Okay. Grab you a paper bag. I should have one more person that doesn't have a partner. Power box. Okay, wonderful. You and I will partner. Okay? I'll have you hang on to the bag for right now. You guys can peek in the bag if you want to. There are 4 red and 2 yellow Starburst in the bag. We are going to play a matching game. Because we're in pairs, each group is going to play the game a total of 10 times. So each person is going to play 5 times. All right? To play the game, you need to close the bag up, shake it up, so that it's all mixed around. So you want to open it up so that they can actually move around. Then you're going to reach into the bag. You're going to grab 1 Starburst. One Starburst. All right. Make a note of the color, remember it, but then toss it back in the bag. All right, you got red. All right. Close the bag back up, shake it around again. All right, now whoever picked out that first Starburst, the same person reaches into the bag, grabs 1 Starburst. If it is the same color as before, you won the game. All right, so what I want you to do, again, you're going to play 10 times total between your team, between your partner group. I want you to record how many times you get a win in your group. All right? That was your first time. Yep, so 9 more times. 5 each person. Huh? Oh, thank you. Thank you. Okay. I'm not sure. Let me look at my calendar. I can let you know tomorrow when would be a good time. So we got 6 total, 3 for each. Wonderful. All right. When you're all done playing the game, you've done 10 times total for your team. Please bring the paper bags back up here to this green bowl, and if you want a pink or an orange starburst, you may help yourself. Oh, perfect. Wait, no, guys, I got pink and orange in the bullet. No, wait, I don't volunteer. You just can't have So let's take what just happened and start to evaluate. I and my partner had 6 wins total. Based on the results from my group, what's the probability of winning this game? How many games did we play? 10. So 6 out of 10 would be my group's probability of winning, which would be what? 60%. Come on. All right. So we're going to go around and get every group's number. We had 19 students in the room today, plus me makes 20, so we had 10 groups, which means we played a total of how many times? 100 games total were played in the room. That's going to make finding our percentage nice and easy. All right, I need somebody, a volunteer with a calculator. Actually, I need 2 volunteers with calculators. Cell phone calculator's fine. We're just going to be adding up all the groups' numbers. You got one for me? And then I need somebody else to double check. Thank you. All right, so we're going to get numbers from all the groups as far as how many wins there were. We're going to put my number in first. We were 6. All right, and then, okay. 3 wins, okay. 6 wins. 5 wins. 5. Back here. 6. 4. 7. 6. 5. All right, what's you got? 53. 53. All right, so we had 53 total wins in the class. So based on the results of the whole class, what's the probability of winning the game? 53%. The numbers worked in our favor today. We had exactly 100 games played, so that made it nice and easy. How could we improve our estimate of the actual true probability of winning? More trials, so play the game more, right? What is that using? Like when we say we're going to play the game more, we need more trials, what concept is that? Law of large numbers, yes. All right. I want you guys now to work either on your own or with your partner to fill in this table. We want to determine the true probability. We're estimating it by playing the game a bunch. And if we played this, I don't know, if I had everybody in the room play the game 50 more times, we would probably get much, much closer to the true probability of winning. But I want to calculate what this true probability is. So how many candies total were in the bag? 6 total candies. What colors were they? Red and yellow. 2 yellow, 4 red. So when I think about reaching into the bag the first time, that first candy, I could have gotten one of the red candies, another red candy. Any one of those 4 red candies might have been what I grabbed, right? Like if you think of them as being numbered, red number 1, red 2, red 3, red 4. And then we had the same kind of thing, but for the yellows, there were 2 possible yellow candies. And after you drew out the first candy, what did you do? Put it back in. So when we go to reach into the bag again, there are how many total candies? 6. 4 of them are red, and 2 of them are yellow. In this space here, this is what I want you to fill out. This would be the results at the end of like, what were the 2 colors that you got? So we're going to do rows and columns. If I'm looking right here, this row and this column means I grabbed what on my first trial, my first candy draw? Red. And on the second candy draw, I got red again. I want you guys to fill in the rest of the table like that. Put the rows and the columns together so that you can fill in the rest of this table. Kind of. Very kind of. Hopefully you guys are winding down, getting your table filled in. It should look like this, right? Circle the outcomes that have 2 reds. On your paper, I want you to circle all the ones that have 2 reds. So like this one, this one. This is all the possible ways you could draw 2 red candies out of the bag and win the game by getting 2 reds. What's the probability that you win this game by getting 2 red candies? What's the probability? 16 out of 36. There are 16 red squares out of a total of 36 squares. If you change that into its decimal form, that comes out to be 0.444. 44444. It's 44 repeating. Could you reduce that fraction down? Yeah. So here's the thing though, when we deal with probabilities, most of the time we don't reduce our fractions down. Because the numerator, that 16 has meaning. There are 16 different ways that you could get 2 reds. And that 36 on the bottom also has a meaning. There are 36 total possible things that could happen when you reach into that bag. So typically we don't reduce that fraction down. Often we'll change it into a decimal so I can turn it into a percent easily. But we don't typically reduce fractions when we're dealing with probabilities. What's the probability that you win by getting 2 yellows? 4 out of 36. We've got 1, 2, 3, 4 out of 36. Does anybody know what that is as a decimal? Yep, 0.11. It's actually 0.1 repeating, but 0.11 would be fine. So if there's 16 out of 36 ways that I could win by getting red, red, and there's 4 out of 36 ways that I could win by getting yellow, yellow, what's the probability of just winning? 20 over 36. We're going to add the 16 over 36 and the 4 over 36 to get 20 over 36, or 0.5 repeating, 0.55. Before I do anything else, did this much make sense? How we got these numbers? Okay. This is our kind of like basics of probability rules. We do need to talk about proper notation for probabilities. How do you write down what you're doing so that the reader understands what you're trying to communicate? So when we do a probability, we always start with a big capital P and then a parenthesis. The capital P stands for probability. Inside the parentheses, we're going to put the event that we are interested in. Up here, this 16 out of 36 was the probability of getting 2 red candies, right? So my first is red, and my second is red. Making that table, filling in the pieces on the table, took a little bit of time, didn't it? Do you want to have to make a table like that every time we're calculating probabilities for 2 events? No, in this case, it's 2 events put together, first candy draw and then a second candy draw. I don't want to have to make a table like that every single time we need to figure out probabilities. It's going to take forever. Does anybody see what we could do to get this same 16 over 36 without having to do the whole table? 4 out of 6. 4 of the candies were red out of 6 total candies on my first draw. 4 out of 6 for my second draw. And if you do 4 over 6 times 4 over 6, you get 16 over 36. All right, this and right here. I'm going to show you guys the symbol that often gets used for and. It looks like an upside down letter U. It's also called the intersection. So this event and that other event both happening at the same time. We use an upside down U for the and. So what could I have done down here on part B to get that 4 out of 36? 2 out of 6 times 2 out of 6, yes. And my probability statement has me getting first yellow and second yellow. 2 out of 6 times 2 out of 6 gives me 4 out of 36. And again, this symbol right here, often we use that upside down U instead of writing the word and. Down in part C, the overall probability of winning. Could you win by getting 2 reds and at the same time in the same game win by getting 2 yellows? How many starbursts do you draw out for one game? You draw out 2 starbursts, and then it's the end of the game, it's the other person's turn, right? Could you get 2 reds when it's your turn, and in the same game, before it's your partner's turn, get 2 yellows so that like you win twice? No, that's not possible. So we're not looking down here when we want to know the overall probability of winning. I'm not wanting to know the probability of 2 things happening at the same time. I want to know the probability that you win by getting 2 reds, or you could also win by getting 2 yellows. So my probability notation for this one, probability of win with red or win with yellow. This or word, we also have a symbol that often gets used for this one. This one just looks like a regular capital U. It does not have the stick on it though. Don't make it look like a lowercase u. Just a big capital U here. This is also called a union. Whenever we are calculating probabilities, you have to write down a probability statement. So a capital P, put inside parentheses, what is it that we are calculating the probability of? And then you can give what that value is. Sometimes you'll need to multiply different fractions together. Sometimes you're going to be adding. If we're adding fractions, what do we have to have? Have to have a common denominator. Let's flip this over. When we made that table, we drew the sample space for this game. The sample space is a list of every single possible outcome. Every possible thing that could happen is my sample space. To find the probability of an event, we take the number of outcomes that result in that event, so 2 reds or 2 yellows, over the total number of outcomes in the sample space. There were 36 total things that could happen in the game. Up in my numerator was how many of them resulted in me winning by red or winning by yellow. In order to do this kind of probability setup, all the outcomes must be equally likely. What do I mean by that? What do I mean by equally likely? What was the probability of grabbing any one of those starburst in the bag? One out of 6, right? Every time you reach into the bag, because there were always 6 starburst in the bag, any one of those 6 starburst had the same chance of being picked. It's not like one of them felt different, so you could kind of move around in the bag and find that one that was a little odd. Same probability. All the outcomes were equally likely. This one we haven't talked about, but you're going to use this in the check your understanding. The complement. Complement is not. So if the probability of winning by getting 2 yellows is 0.11, what's the probability of not winning by getting 2 yellows? If the probability of winning by getting 2 yellows is 0.11, what's the probability that you do not win by getting 2 yellows? 0.99, right? Or 0.89, sorry, I did my math wrong. 0.89. You do 1 minus whatever the probability is. So whenever we want to know about not, and we use this notation right here for the complement, so that would be my not, it's 1 minus the probability that it did happen. Probability of A and B, there's that symbol. This means that both events have to occur. When we talk about an or, a union, it means one of these 2 events had to happen, or they could both happen, that's okay too. In the game that we just played, you couldn't win by getting 2 reds and 2 yellows at the same time. But when we use a union, because some situations you can have both happen at the same time. This one happened, or this one happened, or they both happened. That's what my or represents here. I want you guys to take about 5 minutes to do the check your understanding. There are 5 questions there. I want you guys to take a couple moments to do that. Like I said, take about 5 minutes. Would like to work with somebody else and bounce your ideas off of them, that is perfectly fine. You may work together. Yes. Of the mothers that they interviewed had 3 children. Exactly. 13% of the mothers that they interviewed had 4 or more kids. So we don't have the sample that they talked to. They're just giving us like the probabilities, the percentages that they had after the fact. Does that make more sense?
Yes, but I don't understand why I know this is incorrect, but I don't know how to do it. If that makes sense. Or maybe I don't think it's 1 out of 4. What is 1 out of 4 is the best? 25? No, that's 40.
talk to a bunch of people, right? Four or more has less than everybody else, right?
Yeah.
Not exactly. I hear what you're saying. I don't think you're focused on the right piece there. If you guys are struggling with number one, hop on to the others.
Okay.
Don't waste all your time on number one. If you're struggling with what to write down for number one, hop on and look at the other questions. You don't like it?
No, we did. I think it was algebra 2 weeks. I was like, it was not my bag. It was not my bag at all. But the one test I didn't get on.
There's some similarities between what we did yesterday and this, yes.
1 minute, but it ain't there yet.
It's not all the way there.
No,
That's okay.
It's not cooking.
Not done baking.
Let me look back. That gave us the problem.
I don't like this.
No.
You can leave it as a decimal.
So I'm doing something right. I'm cooking the big because I'm looking at it's on the stove. Okay.
All right, let's talk about number one. Then we'll go look at the other ones. Let's go look at number one. Where did this 1/4 come from? Like, how did he come up with that number? There's 4 outcomes. A mother either has 1 child, 2 children, 3 children, or 4 or more children. Why is 0 not up there? Because then they wouldn't be a mother. Yes. So the very beginning would have to be 1 because they're a mother. There are 4 total options, and this is 1 out of those total options, right? You guys ever known families that are really big? Is everybody in the United States equally likely to have that large of a family? No. The reason that he's wrong is that there's a 22% chance that all of the mothers in the room, there's 22% chance that if I pick one out, she's got just 1 kid. It's not an equally likely situation. Not exactly 25% of the mothers in the room had just 1 child. We do not have equally likely outcomes. What is the missing probability? The probability of having 2 kids? Yep, 0.41. Now, tell me how you got that. Yep, that's exactly right. Most of the time, when I'm writing probabilities down, just to keep the symbol, like to keep it from being too much on there, so I don't have to write the % symbol each time, I write it down in its decimal form. There's nothing wrong with doing it in its percent form. But you would do 1 or 100% minus all the other possible outcomes, those probabilities, because this would have to add up to 100%. It has to add up to 1. And so we get 0.41. So far, so good? All right. What's the probability that a randomly selected mother has less than 2 children? 0.22, right? Less than 2 children would mean she doesn't have 2, she doesn't have 3, she doesn't have 4 or more. So she would have to have just 1 child, so 0.22. What's the probability that a randomly selected mother has 1 or 2 children? What do you say? 0.63, absolutely correct. 1 or 2 children. So you could do 1 union 2. That would be another way to write your probability notation. And it is 0.63. What is the probability that a randomly selected mother does not have 4 or more children? What did you say? 0.87. There's 2 different ways that you can get to that number. One of them will consistently be faster in each situation, doing a 1 minus. This is an opportunity for us to use our complement notation. 4 plus children complement. So we do 1 minus the probability that this does occur. The other way that you could have done it is you could have added up all the other possibilities. But sometimes we're looking at situations where there's like 15 outcomes. And I want to know, what's the probability that it's not this one? I don't want to add up those other 14 numbers. So just do 1 minus the probability that it did happen. So far, so good? All right, that wraps us up for today. The homework that you guys grabbed on your way in the door is due on Friday. And I really would like you guys to do some reading tonight so that you are ready for our lesson tomorrow, because we're going to continue working with probabilities tomorrow. Pages 342 to 353. It's 11 pages. 342 to 353.